Morning, everybody. Today is the last lecture of the mini course by Shota. I will continue talking about perhaps confinement in QFTs in AdS. Thanks.
All right, thank you. So yes, so let's continue the discussion from yesterday. So yesterday, like we were discussing like a YAML theory in AdS, and in particular, I was pointing out that if you go to the weak, if you choose the Dirichlet boundary condition and go to the small AdS radius, the theory is in some sense deconfined because you see the color non-singlet degrees of freedom. But something has to happen at the intermediate AdS scale because we know that in the flat space, the theory is in the confining phase. And there are several proposals in the literatures how this kind of phase transition happens. And I reviewed the three scenarios. And the first one is called Higgs mechanism. The idea is that some scalar operator, which is in the joint representation of the gauge group, becomes marginal at some point. And the dimension hits 3. And then afterwards, it can actually show up in the right-hand side of the conservation law of the current. And together, they combine into long multiplet. And then these current now becomes massive and then can have a very large mass in the flat space limit. However, although this is not a very strict argument, like I pointed out that I said like this is not so favorable because it seems like it leads to many states, too many states as compared to what you expect for the flat space limit of the YAMLs in AdS. And the second scenario is that maybe the two-point function of the current, especially this Cj, which controls the two-point normalization of the current, goes to 0 at some point, and then the currents decouple from the theory. So this is a kind of way to lose, one possible way to lose the non-singlet degrees of freedom. So here, well, this seems plausible. I'm going to mention whether this is really plausible in the actual YAMLs or not. And the third one is what is called a tachyon. So the idea is that maybe at some point, at some AdS radius, the scalar operator, there's some scalar operator whose dimension goes to 3/2. And a 3/2 is kind of like famously known as the BF bound because this corresponds to the minimal possible mass square in AdS. And beyond that, maybe there might be some tachyonic instability. However, this BF bound and this instability analysis was done in basically solving the Klein-Gordon equation in AdS, so it's very perturbative analysis. And from non-perturbative CFT point of view, this delta equals 3/2 is certainly well above well above unitarity bound, and it's kind of like hard to imagine something weird happening at some like a random point in this delta plane. And yesterday, Liam already pointed out that however, there is something special happening when the scalar operator hits delta equals 3/2. And that is that if you consider the double trace operator, that double trace operator has a dimension 3 if the theory in the bulk is kind of weakly coupled. And indeed, there is, in some sense, like a non-perturbative version of this tachyonic instability. So this is the fourth scenario that I want to advocate. And I do, and then this is a kind of like the scenario that we discussed in the paper with Christian and Lorenzo from and then Zimin in last year. And this we call marginal singlet scenario. And let me just write down what this is. So in this scenario, a scalar operator, which is singlet, in this case singlet under SUN group. So let's call it O singlet, becomes marginal at some, and then afterwards, so this operator in the small AdS radius is actually irrelevant, but at some point it hits marginality and afterwards it becomes relevant. And because this is a relevant operator, it triggers RG flow and destabilize the original boundary condition. So this is a scenario that we discussed in the that we proposed or advocated in the paper. So that roughly speaking, what you would expect is that there is some operator which is irrelevant initially, starts having negative anomalous dimension, and at some point it hits marginality, and the boundary condition is gone. And the best candidate of this operator is actually a trace of J mu J mu. So clearly, this is a singlet operator in SUN. In addition, it is a singlet operator. It is a scalar operator. And then this operator, if you just count the dimension at weak coupling, it has a dimension 4. And the expectation is that like it must have a negative dimension. Yeah, okay, that's a very good question, and I'm going to comment on that. And there is actually like a very nice result, which basically shows the instability, and that's in the paper by Bolt and Eduardo Loria.
I have issues with how you draw this curve.
Sorry?
This curve can never cross like this.
Okay. You mean it's more like this?
Yeah.
Okay.
And this also answers the question of Peter.
Okay. Yes.
So in fact, the issue is not that triggers the RG flow, but it's just at this point, there's going to be an annihilation of two CFTs, and the CFT will just disappear. So for a CFT to annihilate with another CFT, there has to be a marginal operator. So annihilation can only happen at this point.
But I think like after this, like there is some like a different direction. Like isn't it natural to expect that the same operator basically takes you to some other fixed point?
No, there's no fixed point.
Right, like so there is an, okay. But maybe we should discuss it like after I mention this. Explain this.
Sorry, why can it? Sorry, Sal. Why did you say that can it just cross like Shota drew originally?
Right. So let's first explain the fixed point merger scenario story, because so this kind of behavior. So there are several comments that I wanted to make. But before talking about the fixed point merger, let's talk about let's address the comment by Liam yesterday. So in weakly coupled theory, and so if there is a tachyon, which is delta equal 3/2, then that means like a double trace operator or a two particle state have dimension delta equals 3. So in some sense, like you can think of this as a kind of like a non-perturbative version of the tachyonic instability. So this kind of includes the tachyonic instability when the theory is weakly coupled. Okay? And so another comment is that this behavior that some operator hitting marginality and you lose the fixed point. So this is often coming from generically it comes from fixed point merger and annihilation. So what do I mean by this? So it's precisely based on the paper by Slava and Victor and Bernardo. And well, that's one paper which discussed this point very clearly, although many other people also discussed it. So let's imagine that like we have some theory with a coupling constant lambda and a there is a beta function. And so this kind of like so the question is, what is a kind of like a typical setup which gives rise to some CFT with a continuous parameter, and then at some point of the parameter space, the operator becomes marginal. And generically, this happens when you have a beta function like this. And then as you change the parameter of the theory, this beta function, this height becomes smaller and eventually becomes like this. So let me explain what I mean by this. So if you have a beta function like this, of course, you see two fixed points. And the flow, and then starting from this fixed point, goes like this. So there is some relevant operator around this point. And then that, if you perturb it by that operator, you go to somewhere here. And so this is a UV fixed point and a RF fixed point. And as you change the parameter and then as you decrease this height, then the flow becomes shorter and shorter, which basically suggests that, which basically means from the point of view of the dimension of this operator, relevant operator, it means that the dimension of this relevant operator becomes marginal. Or from the point of view of this CFT, it means that this irrelevant operator becomes closer to marginality. So if you plot the dimension of the operator as a parameter, let's call it t, then it precisely is going to show something like this. So on this side, so let's call this CFT A, and then this called CFT B. So this side is the dimension of that operator from CFT in CFT A, and this is CFT A, sorry, CFT B A and a CFT B, and then there is a RG flow like this. Okay. And so when this happens, after this happens, of course, like if you go to the complex plane, there is a still fixed point, and that's where you start seeing the complex CFT. But if you want to have a real unitary boundary theory, what happens is that after this point, you just lose the fixed points or CFT or boundary conditions, and that's the fixed point merger story. Okay, so this is one possibility of how you can lose the original boundary condition. And then, but you can, when I was explaining this, I was saying the words generically, this is what you expect, and then this is one typical setup. But then you might ask whether this is really going to happen in the setup that we are analyzing. But fortunately, there is a more direct argument in this setup of QFT in AdS, which was discussed in this paper section. I forgot the number of sections, but in this paper by these authors. So, because of the lack of time, I'm not going to explain you the details of the argument, but let me just explain the setup. So setup is of course a QFT in AdS. So we consider QFT in AdS, and with coupling constant. And then there's some one parameter family, let's call it T, and then you deform the theory by this, O of X and Z. So I wrote explicitly X and Z in order to say that this is really a deformation inside AdS. So Z is the radial coordinate. Okay? And furthermore, let's assume that there is, well, this is of course one can always do. And then you expand the operator in the interior of the AdS in terms of the operator at the boundary. This is always something that you can always do. Which is guaranteed by the isometry of AdS. So let's call the leading operator that you see O hat, and denote the dimension of the operator by delta hat. And so this is of course the dimension, which also depends on this coupling constant T. And now let's imagine the situation. This delta hat T hits marginality at some point TC. So, and then what they showed is the okay, maybe let's keep this for a while. And then what they showed is the following. So let's imagine we do have some like a nice boundary condition preserving AdS isometry at precisely at t equal tc. Then the question they asked is, can you actually preserve this nice property like AdS boundary condition when you slightly deform t away from tc? Okay? And basically, so now let me go to the conclusion of what they did. So the conclusion is that if you slightly deform away from TC, TC, okay, T equals, now T equals TC plus delta T. So then, of course, like from the point of view of the boundary CFT defined at TC, the theory is deformed by this delta T.
Shota.
Yes.
Do you see this happen by looking at equations of motion in the bulk, or is this a field theory analysis where you compute beta functions and so on?
Right. So this is more like a usual conformal field theory analysis, like imagining some local conformal field theory on the boundary.
So conformal perturbation theory type
right.
calculation?
So this is more like coming from conformal perturbation theory.
Okay.
So,
thank you.
So again, like this is another subtlety of applying this logic directly to our setup, because precisely speaking, like we are deforming the bulk, not the boundary. So that's why like I also wanted to mention this paper, which directly addresses this setup. Okay, so what they do is to deform the bulk by around a TC point. Then, like of course, like a theory gets this extra perturbation, but in order to maintain the finiteness of the beta for all the correlation function, by using the kind of conformal perturbation in the bulk, probably I shouldn't call it conformal perturbation, it's some perturbation in the bulk, you can also say that you also need some counter term which absorb the divergence. So this is our AdS. So where epsilon is some cutoff near the boundary. So I'm imagining doing the like a IR cutoff near the boundary, which one always do in the context of AdS CFT. And you can show that this, to maintain the finiteness of the correlation function, you need to do something like this. Sorry. You need to introduce this counter term with some number. So this is coming from requiring the finiteness of the correlation function. So once you make it finite, but you still need to ask whether the resulting correlation function preserves the AdS isometry. So this only guarantees that it's finite, then you need to check the word identity. And if you start checking the word identity, then it turns out that actually this counter term is not enough, and you actually need to have a precisely fine-tuned finite counter term. So this is a divergent counter term which absorbs the divergence, but it turns out you also need to add the finite counter term. Sorry, like maybe I should write d plus 1 here. So this is the bulk perturbation, and you are putting some kind of like a boundary counter terms. And so this is needed for conformal symmetry. So basically, or word identity. And requiring the word identity is satisfied, you get the equation of the following form: delta t minus some number times g hat square equals 0. Okay? So this formula is telling you. So this formula is telling you that, so in order to have a kind of unitary theory, you need to make this g hat to be real, because otherwise it leads to complex CFT. So this means that g has to be real, which means that this has a definite sign, which suggests that delta t should also have a definite sign. So the conformality or AdS isometry is preserved only on one side of the deformation. And if you go to the other side, you basically lose the AdS isometry, this boundary condition. This argument more directly establishes the fact that if some operator hits marginality, like so, then afterwards you will lose the boundary condition.
Sorry, I missed the logic. Where do you use the marginal operator in this argument?
So for example, you get this logarithmic divergence. That's coming from the marginality. Essentially, what you do is that you have a bulk expansion,
yes.
bulk operator, and then you deform the boundary correlation function by the bulk perturbation, but you rewrite it using this bulk boundary OP, and then rewrite it as a.
So this argument only applies at the point where there's a marginal
right.
boundary operator.
Yeah, exactly.
Okay, thank you.
Okay. It is. I guess it is true. I don't know if you thought about. But
sorry, can you repeat the question?
Well, my question is why is it obvious that we have some family of theories in AdS and the dependent parameter t. Why changing t only adds to the action this operator O, but not also some other operators?
Oh, it does. I mean, the only one that, if there are relevant ones, you have to tune the coefficient to 0 to maintain conformality of the boundary. And so, yeah, there could be further relevant ones, but they don't lead to this delicate thing where you have to tune some coupling to retain conformal invariance. Right? I think it's very similar to your paper. The only difference, so maybe we can say the words that these are infrared divergences, not UV divergences. But as people who are familiar with AdS CFT know very well, the structure of infrared divergences is just like that of UV divergences in general quantum field theory. So despite the fact that we're talking about a completely different type of divergences, you can still say beta function, anomalous dimension, and all of that. And so then your analysis basically applies there automatically. So you see that to maintain conformality, you have to tune your coupling. And at some point when a coupling crosses threshold, the tuning has to be at an imaginary value of the coupling, or you lose conformality. And that's what happens here.
Why do we want conformality?
So, okay.
Does the fact that we can't impose some boundary conditions where the correlators on the boundary look like those of a conformal field theory? If we can't do that, does it mean that the bulk theory confines? Or what is the logic?
Right, so, okay, so this logic only tells you indeed, if you require, so the conformality is from the point of view of boundary, but from the point of view, in the bulk, it's just like a configuration which preserves this AdS isometry. Much like when you talk about the phases of the theory, we normally talk about a Lorentz invariant vacuum. Of course, indeed, this only tells you that the conformally invariant boundary condition cannot exist beyond this point. So, which means that there can be some inhomogeneous configuration can exist. Right, yeah.
Well, that's what allows the current to lift, right? The current dimension is protected by conformal invariance. So if you cannot retain conformal invariance, then you say, yes, now my current can go away.
But does it mean there's confinement involved, or what's the relation?
That's there.
What's the connection with confinement and deconfinement?
Right, yeah, so, okay, if you start talking about inhomogeneous phases, right, so maybe you can find some.
Homogeneous only in AdS, right? But once you take the flat space limit, I don't know, maybe some. Maybe
Okay, yeah.
On a point in the bulk, it will still be homogeneous.
Right.
Maybe you want to say that if
That is true. Yeah, so maybe like what I'm addressing here is how the boundary condition, which is homogeneous in AdS and have gluon degrees of freedom and then currents degrees of, which are currents in the boundary, can disappear at some point.
Yeah.
So that imposes a bound.
So that, yes, that imposes a bound. So that like has to disappear, and then like the way it disappears is coming from this like a fixed point merger, or like in other words like a singlet marginality. Okay. Oh. This is a second order. No, like when this happens, like it's oftentimes first order phase transition. Oh, okay. So right. So what? Right. I think okay.
Talking about phase transitions, we just reduced ourselves to a very concrete CFT question. Given a family of CFTs, does it exist for all values of a certain parameter or not? I mean, and we are just trying to resolve the paradox which would arise if that family of CFTs existed for all values of the radius. So the moment we show that the family disappears, and it disappears in a continuous way, well, the paradox is resolved. Call it whatever you want, phase transition. Now we can invent some nice words for this.
Yeah, I didn't understand that comment. I thought the starting point of this talk is to understand what happened, how to describe the phase transition of Yang-Mills in AdS.
Okay, so right. So it's true that like we are not really directly addressing the phase transition. I think here what I'm saying is that so even in the case of first order phase transition, at some point like you completely lose this metastable vacuum. So something like that should happen also from the CFT language. I cannot really like logically connect these like a phase transition picture and then this like a disappearance of the CFT, but I would say that this is a kind of analog of like a disappearance of this complete disappearance of the metastable vacuum. Does it answer your question? So what's going to happen after this point is that there is some completely different CFT, and then that's the one which basically corresponds to the true vacuum in the sense of first order phase transition. And I'm not saying that this new CFT only exists after this point. Like new CFT might coexist even here. And actually, like it does exist here because we do believe that the CFT after this merger point, that like a boundary condition that survives is actually Neumann boundary condition, which you can actually go all the way to the zero coupling. So there is yet another CFT here, and essentially after this point, like the only boundary condition which survives is the Neumann boundary condition, and then that is the one which survives. Yep. Mm-hmm.
That's enough to tell you whether or not this is going to be some first order or second order transition. Like you can look at the energy, the AdS energy, and see whether you're picking up some imaginary piece that signals some instability.
But one thing I can say is that like after this transition point, there is no
I
CFT,
agree.
so there is nothing continuously connected to this point.
So you're saying you can't use the dynamics of that mode to talk about how AdS is becoming unstable here, and you're jumping to. Okay. Thank you.
I think that's a more interesting thing. Well, if you really want to like get the flat space physics. But I just wanted to point out that this is a kind of like a simpler question which can be phrased in terms of CFT. And this is probably actually more easier question if you want to bootstrap, because this is a question of whether boundary condition exists or not, which Bootstrap is like very good at answering.
No, but I'm still, I don't understand, Silvio. So you agree, I mean, Neumann condition, we can study that, but I think the paradox arises if you have both Neumann condition for all values of the radius and the Dirichlet condition for all values of the radius. That would be paradoxical. Then you wouldn't know which one to choose, and also the Dirichlet one would, its existence for all values of the radius would suggest that QCD remains deconfined. And so now we solved the paradox, so Dirichlet condition, we can now discard it. Now we can be happy and study the Neumann condition and try to learn something about the confining phase of QCD. That's the way I understand it.
Okay, maybe indeed, that's a very nice way to put it. Thanks. Yes, indeed. Now the next goal will be studying Neumann boundary condition. I will leave it to exercise for audience. Yeah. Right. Yeah. Right. Yeah, exactly. All right, so now, so I presented several scenarios, and 1, 2, 3, 4. So let's just 1, 2, 3, 4. And I was already saying that like 1 and 3 are not very favorable because like 3 is very perturbative and 1 seems like leading to a lot of degrees of freedom. But we can also kind of like try to see what's really happening in Yang-Mills in AdS4 by doing perturbation theory. So now this is the perturbative test of Yang-Mills in AdS4. And then this is just like summarizing the result of the paper, which appeared this week. And not by me, by Ricardo and Lorenzo and Fabiana and Marco Cerrone. And so let me just first draw this picture. So the result is like this. So if you choose the Dirichlet boundary condition, as I said, there are at weak coupling, there are scalar operators that you can easily construct, which are made out of like 2 J's, J mu, J mu. But in each one is in the joint representation of SUN. So if you multiply the two, like it can have like several different operators. It can be several different operators depending on the representation of the gauge SUN group. And what they show is that they explicitly computed anomalous dimension of all these operators and then found that there is only one guy which goes down. And then this is the singlet operator, trace JJ. And all the other one, for example, the adjoint ones, which I was talking about in the context of Hicksing scenario. So for the Hicksing scenario to work, this one needs to go down and hit that marginality. But what they showed is that actually you can, if you compute the anomalous dimension at one loop, it goes up actually. So this indicates, this is of course like not the full answer, not the complete answer, because it's just a one loop computation, that this indicates that Hicksing scenario doesn't seem to be happening. And furthermore, let me see. So they also looked at when just like extrapolating one loop answer, and then they estimated when this operator hits marginality. And then that happens at lambda critical, where lambda is a 2-foot coupling, GM mil squared times n critical. around 21.5. Okay? This seems rather large, but translating this to the RADS times lambda Young-Mills scale, so this, after the translation, this is not so big. Okay, but anyway, this is a one-loop answer, so whether you take it seriously or not, it's up to you. But the reason why I wanted to show this number is that they also checked they also computed the one-loop correction to CJ. And then, again, checked like when this CJ hits 0. So this is relevant for this decoupling scenario. And then what they got is that this happens, so this lambda critical for the CJ is actually much, much larger, which is 272. So this basically suggests that marginal singlet shows up earlier than decoupling. So this basically favors, in some sense, the marginal singlet scenario over decoupling scenario, which was the only like a remaining plausible scenario. Only other remaining plausible scenario. Okay, so
sorry, I'm a bit confused. So why are we expressing our result in terms of lambda critical? Yeah, what is lambda critical? I don't understand.
Sorry.
No, I mean, I understand the equation that you wrote,
right.
RADS lambda Young-Mills. This makes sense, but why? Yeah, what is G Young-Mills? What is G Young-Mills?
Oh, so
is it supposed to be G Young-Mills at which scale in that formula?
Well, I guess like it's supposed to be G Young-Mills in the AdS scale.
Ah, the AdS scale. Okay.
So like yeah, lambda critical, you should translate this to our AdS.
Okay.
So like roughly speaking, lambda equals 0 corresponds to here, and then lambda goes to large as you increase our AdS.
But so then the transition happens still. Usually in QCD we don't give G Young-Mills squared, we give G Young-Mills squared divided by 16 pi squared or something like that. So should are two loop corrections small at this value of G Young-Mills
right, so this
squared, or is it still in the perturbative regime?
Right, so that's the claim. So you do also here you should divide by 16 pi squared.
Yeah.
So that's why this can be rather small, not very small, but it's relatively small.
Yeah. And so is there an estimate what two loop correction would change this result?
Well, I guess that hasn't been done, and it's a little more complicated computation. Well,
no, man, to compute it would be very hard, of course, but is it like...
Ah, okay, but here, so this was rather small if you divide by 116 pi squared, thanks to the a numerical coefficient of the anomalous dimension. So a one loop anomalous dimension comes with a relatively large numerical coefficient, and that was the reason why this transition happens at a rather small point. And at two loop, we don't know, so.
But we know that somehow all the square roots should develop, right? So all terms in perturbation theory, you will never get the square root behavior. So somehow still all terms should become important.
That's a good point indeed. Right. But maybe, the leading answer is predicting something like this, but maybe if it becomes square root, it might actually happens earlier, which is more favorable scenario. Okay. Right, so Now I need to decide.
So I have a question. Maybe
Yeah.
is there a group theory factor that puts the other two representation with the beta function, which is positive, or just
Yes. Okay. Okay. Thanks. Okay. All right. So. I have like 30 minutes, so a little bit more than 30 minutes, I guess. Right. So let's see. So they computed this basically using direct perturbation theory, but in addition, there is actually like a faster way of computing the anomalous dimension of this guy. So now let me just briefly review the computation. Or should I review the computation? Or go to the last topic of the lecture? What do you think? Okay, so both decided, so I'm going to the topic 3. So if you want to know more about the how, there is actually, okay, let me just write one nice formula, and then if you're interested, please ask Ricardo sitting there. So there is a nice a rather general formula of, so here like I'm just writing it for trace JJ, but it's actually like you can kind of like a generalize to more general context in which like you start from CFT in AdS and then perturb by some operator, marginal operator. Oh, and in that situation, you can actually write the anomalous dimension in terms of bulk beta function. So, well, this is some kind of, well, this is some, yeah, let's just write it, OD, lambda, CT, D lambda, and delta of D. So let's just write like this, and then D. So this D is, what is this D? So this D is that if you just put a CFT in AdS, it's the same as CFT on a half space after the Wow transformation. So there is another distinguished operator, which is called displacement operator. And this formula basically tells you how the displacement operator acquires a one-loop anomalous dimension if you perturb the bulk CFT by margin operator. And the nice thing about this is that it is basically proportional to the beta function. And this actually like allows you to do the computation of the trace JJ. So in this context, the trace JJ turned out to be precisely the displacement operator corresponding to free Young mills in AdS4. And using this formula, you can just recycle what people computed for the beta function in Young mills in flat space, and then immediately compute the dimension of the operator, one loop correction to the dimension of the operator. And the derivation, if you are interested, please ask him. And now I'm going to, in the remaining 30 minutes, I'm going to change the topic completely. So, but before doing that, any other question? Yeah.
Is this analogous to the Hagedorn transition? Is this the AdS version of the Hagedorn transition where I put the theory on RD minus 1 times S1, as I change the radius of S1, something happens. It's deconfined for small radius, confined for large radius. At some point, something happens.
Yeah, I would like to say yes, but I cannot make a more quantitative argument.
What do we know about the other CFT that merges when this one disappears?
That's a very good point. So I talked about the merger. So I said like there is some, this Dirichlet boundary condition merges with something. So this Dirichlet twiddle, there should, so that if this, so this singlet marginal condition scenario suggests that there is yet another boundary condition which merges with Dirichlet and then pair annihilate with Dirichlet. Actually, we have zero idea what that is, and we really want to know, but at this point we really honestly don't know about it at all. So this is mysterious, at least to us. All right, so in the remaining 30 minutes, I'm going to the topic 3, which is about modified crossing. So the reason why I'm talking about this in this lecture is that you can think of it as a kind of like one additional subtlety about taking the flat space limit. And so, yep.
Why can't it be just some sort of SUN invariant, non-local CFT, which comes from any other bulk theory?
Right, so maybe the answer, the question we want to ask is, first, whether does this CFT exist all the way down to the weak, very weak coupling? And if so, what is the kind of like Lagrangian way of describing it? So that we don't know. So that's what I mean by mysterious.
Yeah.
Mm-hmm. I see. Right. JJ, but JJ always have dimension 2 times z minus 1. And so you're asking like to d. Okay, d equal to 2 plus epsilon. The bulk 3 plus epsilon. Okay, yeah, that's a good point. Yeah, that's a good suggestion. Yeah. Okay, I'm not sure what I'm gonna do now, but so okay, and let me just write a punchline of what I'm going to talk about, what I'm hoping to talk about. So the punchline is that like so now I'm completely changing the topic. Well, although like there is some relation to flat space limit, which I'm hope to mention in the end. So now I'm talking about purely scattering matrix. Like AdS only plays a kind of like a not the main role, but it does show up in the argument. So the punchline of what I'm going to talk about in the remaining 25 minutes or so is that in some theories with non-invariable symmetry, there are actually examples in which S matrix seems to violate the usual crossing symmetry. And more precisely, I'm going to talk about integrable flows in 1 plus 1D to gapped phase. And the reason why I'm talking about this is that this, you can think of it as coming from a difference of kind of normalization or difference of basis between CFT and flat space, difference of basis in flat space and or AdS, or which is basically equal to CFT, boundary CFT, which I briefly mentioned, I think, yesterday, about how to define the orthonormal basis by taking the flat space limit of conformal AdS. And so to do that, in the next 5 minutes, I'm going to give a super quick summary or review of what the non-invariable symmetry is. Okay, so let's see if I manage. And so probably you heard many times the word non-invertible symmetry, and you probably also know what they are. But the reason why many people are interested in the kind of generalization of symmetries, non-invertible or higher form, is that, those basically came from the realization or that actually symmetry operators in QFT is nothing but a special case of topological operator. Okay, what I mean by this is that, for example, the symmetry generator or the charges if you have a global symmetry with native current, the charges or symmetry generator can be expressed as exponential of the integral of the conserved current integrated around the codimension 1 surface. And then this surface can be smoothly deformed thanks to the fact that this current is conserved. So this, you can just change the shape like this. And in particular, if you move this curve in the time direction, that basically corresponds to the conservation of charges. Okay? But the important point is that in QFT, there are many more topological operators than the usual symmetries. And those actually play the same role as the symmetry generators, and those are often called non-invertible symmetry or higher form symmetries. And so the one difference from the usual symmetry and the non-invertible symmetry is that in the usual symmetry, all these lines are basically labeled by some elements of the group. So let's call it G of A, and then that's in the element of the group. And you can multiply them, and then they basically fuse following the group multiplication laws. On the other hand, so then importantly, because it follows the group multiplication law, on the right-hand side, you always find one quantity here, single quantity here. On the other hand, if you consider more general topological operator, in particular, let's talk about the 1+1 dimension, and then it's called these non-invertible symmetry are often called a fusion category. And that satisfies a more non-trivial fusion relation. And in particular, you have multiple objects and a sum of multiple objects on the right-hand side. And furthermore, this is just some number, and this number needs to be positive, non-negative integer. And the reason why this is non-negative integer is because this has an interpretation as the size of some Hilbert space defined in the junction. And so that's why, the number of states, or a number of, so that's why it has to be a non-negative integer. But I cannot really have time to explain the details of that. And the data that characterizes, so in 1+1 dimension, let's just write it explicitly that this is 1+1D. So in 1+1 dimension, the non-invertible symmetries are basically given by what's called fusion category, and that was well-studied object. And the data that characterizes the fusion category consists of the following. So first important data which characterize the fusion category is, of course, this fusion coefficient, which basically determines the multiplication, how the things can be multiplied. And in particular, this also governs not just how you can multiply the lines, like a line defect, topological line operator, but it also governs whether you can form a junction between different lines. So if this NABC is non-zero, you can form a junction. Okay? And another important quantity which shows up in the discussion in the fusion category is what's called quantum dimension, which is basically the expectations value of the circular line, and which I'm going to denote by D of A. Okay, and finally, the there is an analog of the fusion kernel in conformal field theory, or a 6J symbol in the fusion conformal field theory, which relate basically different network of lines. So you can like relate different networks of line using what's called F symbol. So you can think of it as an analog of the CFT 6J symbol. Okay, and all these satisfy non-trivial consistency conditions. For example, one of the consistency condition is easy to see. For example, like if you consider this kind of configuration, you have like a circular line A and a circular line B. You can evaluate this in two different ways. So in one way, you can first shrink A and then replace it with the expectation value, and afterwards you can shrink B. That leads to, of course, dA times dB. On the other hand, you can first fuse A and B and write it as a sum of like different lines and then shrink it. So that leads to this expression. So this is a kind of one constraint imposed on these data. And there are also some other constraints involving F symbol, and especially there is a famous pentagon identity, which I'm not going to talk about. Okay. So now, let's talk about, so here, like what I have been talking about was sounded probably a little bit abstract. But now let's talk about the example of theories with non-invertible symmetry. And there is actually in 1+1D the famous and the simplest example with non-invertible symmetry, which is 2D easing at critical point. So let's draw the famous phase diagram of the 2D easing model. So 2D easing model has a temperature T, and at T equal Tc, it flows the conformal field theory, and in the high temperature phase, it is disordered. Whereas in the low temperature phase, it is ordered. Okay, the symmetry gets spontaneously broken. From quantum field theory point of view, disordered phase basically corresponds to theory with a single vacuum. So the potential would look like this. Or like I'm talking about this Landau-Ginzburg description of this phase transition. Whereas in the ordered phase, you have this kind of potential, okay? So that is what you expect. Now, you probably also remember that, especially if you in the context of 2D lattice easing model, there is some non-trivial duality between which maps the high temperature phase and low temperature phase. That is often called the Kramers-Wanier duality. And this Kramers-Wanier duality at generic temperature is a duality. It's not a symmetry because it maps a theory with certain temperature to a theory at different temperature, which are kind of like a different series. However, if you tune the temperature to be T equal Tc, this duality really becomes a symmetry because it maps to a theory at Tc to a theory at Tc. Okay, so this is what I'm going to call Kramers-Wanier symmetry. However, there is one weird thing going on about this Kramers-Wanier symmetry because, as I said, like this maps high temperature to low temperature, but like high temperature phase and low temperature phase has different number of vacua. So if you just focus on the action of this Kramers-Wanier duality on the very low energy state, it seems like the map, this duality map is 2 to 1. Okay, so let's call this plus vacuum, and then this called minus vacuum, and this called zero vacuum. So this suggests that the Kramers-Wanier duality maps both plus vacuum and minus vacuum to 0, and then 0 vacuum to the linear combination of plus and minus. Okay? So this is actually how Komatsu duality acts on these vacua. And this already tells you that this is 2 to 1, and then this has a kernel. Action of this symmetry of the duality has a kernel. And the key point is that the Komatsu symmetry, which is just a specialization of the Komatsu duality, also inherits this like a non-invertible property. As you can see, like because the map is 2 to 1, you cannot really come back to itself. And now just let's write it explicitly, the symmetry algebra of 2D Ising CFT. So this is a kind of, probably some of you already have seen it many times. So there are like 3 different distinct line or symmetry line or topological lines into the Ising CFT. And this eta is just a usual Z2. So that's why it squares to 1. But this n is a Komatsu symmetry, and it has this action, and then n eta equal in eta n equal n. Okay? So, and you can just check that this algebra is consistent with the action of the vacua that I wrote in the previous slide or previous page. For example, if you start from 0 vacuum, so 0 vacuum, I said n maps to plus minus. Maybe this is not a good example, sorry. Let's start from plus. And I said n maps to 0. And if you do it twice, n square, so this corresponds to acting n squared to plus, then you get plus minus. Okay? But this to this is precisely 1 plus eta, right? Because eta flips plus to minus. Okay, so now we identified the simplest theory with non-invertible symmetry. So maybe one might ask whether we can study the S matrix by doing the relevant deformation of this 2D Ising CFT and see what is the interplay between non-invertible symmetry and S matrix. However, this unfortunately doesn't work because in the case of 2D Ising model, you can actually check that all relevant deformation breaks non-invertible symmetry n. So you need to do a little bit more something a little bit more complicated. But you actually don't need to do too complicated thing, because the only thing you need to do in order to find the RG flow preserving non-invertible symmetry is to look at the next minimal model, which is a tricritical Ising CFT. And this perturbation of the tricritical Ising CFT was studied in the past a lot, and people have found by various, studying various lattice model and then numerical method, and also using integrability, that if you deform this theory by what's called phi 1,3 operator, whose dimension is 6/5, I think, with certain choice of sign, it actually flows to a gapped phase with 3 vacua. Okay? And let's call this minus and 0 and plus. And this flow turned out to preserve all these 1 and eta and n symmetry. And in particular, this n acts on these vacua precisely in the same way as I wrote here. So n acting on 0 is plus plus minus, and then n acting on plus and n acting on minus is 0. So in some sense, as far as the action on the vacua is concerned, this looks a little bit like a superposition of disordered and ordered phases of the Ising model. Okay? All right. So now, another nice feature of this deformation, so now like we have massive theory interpolating UV CFT to the gapped phase, is another important thing about this phase, this RG flow, is that this RG flow is integrable. RG flow preserves integrability. So there is a more general argument by Zamolodchikov, which says that if you start from CFT and perturb it by phi 1,3 operator, it always has an integrability. And because of that, Zamolodchikov actually already wrote down the S matrix of this model. And what are these S matrix of this model? So Zamolodchikov basically determined the S matrix by solving the Bootstrap equation, like a Young-Baxter, unitarity, and crossing. And those S matrices are basically S matrices of kinks between neighboring vacua. Okay. Oh, is there any stable particle? So in this theory, like it is, I think, believe that there is no such stable particle. And then that assumption is consistent with various checks against like a Hamiltonian truncation and so on. Okay, so these are S matrices of kinks between neighboring vacua, and then Zamolodchikov used a slightly different notation from us. So like he said like he denoted this vacuum 0, and then this middle vacuum 1/2, and this right vacuum by 1, and then these S matrices of these particles are labeled by Mandelstam variable S, of course, which is the center of mass energy. So here, like because it's 1 + 1D, there is no independent T, so you only have Mandelstam variable S. But in addition, you also need to keep track of what these vacua are. So these are word line of like kinks. So, and then you need to keep track of what these vacua are. So in other words, the S matrix has a bunch of indices on top of the Mandelstam variable S, and where this theta is, S and theta are related by 4m squared cos theta over 2. This is the usual what's called rapidity parameterization, which is convenient in 1 + 1D. The 3 vacua I think is coming from more like a Landau-Ginzburg-like argument. Like I think, well, it's not very rigorous, but I think like from the Landau-Ginzburg point of view, like you kind of have an idea how the potential gets modified if you perturb by some operator. Spectrum of, sorry, maybe you should wait for the microphone. But
I don't know if with Hamiltonian truncation or what, but they also computed the spectrum and saw the degeneracy for the lowest states.
Okay, so there is also more direct argument. Okay, so yeah, so all right, so now, and then Zamolodchikov come up with an answer, which is given by this. by solving the unitarity, by imposing unitarity, crossing, and Yang-Baxter. Okay? But one thing, so let me just also say that these dAs are some number which is related to the label of the vacua, and d0 and d1 is 1, and d1 half is square root of 2. So one thing Zamolodchikov didn't check is that whether this S matrix commutes with, preserves the non-invertible symmetry, which is what we expect, because there is already a convincing evidence or argument that this RG flow also preserves non-invertible symmetry. And the funny thing is that we did check that, and so what we did is to whether you put some n defect and then asked whether this S matrix commutes with this, okay? And what we found is that this, if you check it using the Zamolodchikov S matrix, this is actually not satisfied. Okay? So this seems like a paradox. But we also found that if you consider new S matrix, which is Zamolodchikov divided by this factor, so you just remove this factor from Zamolodchikov S matrix, then non-invertible symmetry is preserved. This new S matrix commutes with the non-invertible symmetry. However, of course, there is a reason why Zamolodchikov put that factor. And the reason why he put that factor is because otherwise the crossing symmetry is violated. And indeed, this is a price to pay. And if you use this new S matrix, A, B, C, D, and theta, the crossing symmetry gets modified precisely by this factor. Okay? So, in the remaining 0 minutes, I'm going to explain. Can I take 5 minutes then? I'm going to explain how this modification is natural and how one can argue for this modification. And then that is where the flat space limit, the subtlety of the flat space limit of AdS comes in. Okay, so now let's talk about the derivation. So the key inputs that goes into the derivation are the following. So the key inputs. So the first input is, well, as I already said, RR is gapped. And described by topological QFT, topological degrees of freedom, non-trivial topological QFT with symmetry line 1 and eta. So this is just saying the same thing I already said in a more a bit more mathematical language. And another important thing is that vacua that we are talking about, so these are 3 vacua, are in one-to-one correspondence with symmetry lines. So by this sentence, I mean 2 things. The first thing is kind of like a trivial, we have 3 vacua and 3 lines. So let me just write some one-to-one map. So we have 3 vacua and then 3 lines. And the reason why I wrote these arrows here is because the way the symmetry line acts on these vacua is exactly the same as how you fuse two lines. Okay? So for example, we already said if you act n on the middle one, you get 0 plus 1. But it is very much analogous to this fusion rule that I already wrote. Okay? So that this is a sense in which you can think of the vacua that put one-to-one correspondence between the vacua and the symmetry lines. And furthermore, because of this property, all vacua can be obtained from some special vacuum 0, by which I mean that, for example, 1/2 vacuum, you can get it by acting n line, and then one vacuum, you can get it from 0 line. Okay? Okay, let me just keep it a little bit. Yes, exactly. So the vacua is in some sense a joint representation. And the third input that's important is that word line of a particle, which are kinks, also act like a symmetry line. So this is coming from the fact that all these particles that I talked about in this theory interpolates between neighboring vacua. So in particular, for example, if the particle wall line can map 0 to 1/2, right? And then that is the same as the action of the n vacua, so n line. Okay, and if you start from 1/2, you can either go to 1 or 0, and that is also the same as the action of the n line. So because of this, so for example, if you consider the kink interpolating vacuum A and B, you can think of it, so this configuration, you can think of it as you are putting some boundary condition, A, and then B, here. And then you are putting kink word line, which from the point of view like a very IR topological quantum field theory can be identified with n defect. So this is just like what I just said. But in addition, so here by boundary condition, I just mean that I need to impose a boundary condition that the left vacuum is A and that the right vacuum is B. But I also said that all the vacuum can be obtained by acting the symmetry line. So you can get a vacuum by acting a line, and so that becomes, this picture also becomes this picture. And this is a kind of like an open string, like a cylinder diagram. But if you compactify future infinity and past infinity, you can also think of this as, so this disk with 0 vacuum and this network of lines. So this basically means that configuration of kinks can be understood as a network of lines. Okay, so now I can give you pictorial explanation in the remaining -5 minutes. But okay, so far so good. So I'm gonna finish the derivation here. Okay, I promise. Okay, so now let's try to study S matrix. Let's imagine we want to study this S matrix by taking some flat space limit of AdS. So but now we need to consider some situation in which you keep track of vacua as well, right? Like that's what I said. So from the point of view of AdS, what you would like to do is to, this is AdS, and then this is the boundary of AdS. You start from some kind of like a correlation function of boundary condition changing operator. So here I put like a boundary condition D, boundary condition B, boundary condition C, NA, okay. So that like you put some boundary conditions so that the field approaches certain vacuum at the respective region. So this is AdS2, okay? And then take flat space limit. Okay? If this is everything one needs to do, I would not expect a violation or modification of crossing because it's just some disk 4-point function which is cyclic. You can just like rotate it without any problem. However, there is a small subtlety here because if you do this, the states, in and out states are not properly normalized because of these extra topological degrees of freedom which governs the non-trivial IR dynamics. More precisely, in state, which is like which is obtained by cutting here, would look like this network of line. So as I said, like the configuration of the solitons are related to the network of lines. So BCB, whereas out state is something like this. Sorry, maybe this is a rather a cat. Sorry, bra. Okay. And the important thing is that now, if you consider overlap or norm of the in-state, there is additional normalization, change of the normalization coming from this network of lines. Okay, so if you really want to define the orthonormal, like in-state and out-states, you need to divide this object, which is basically analytically continued and a flat space limit of the disk 4-point function, by the square root of these norms of in-state and out-states. That's very good point. It's a very important point, and it has to be C. Thank you very much. So that means that the correct S matrix is this one, this like whatever the flat space limit is, like this one that I wrote there, divided by square root of the network of lines. So here we have N, N, B, D, C, C, because it's a norm. And then here I also need to divide by the, N, N, D, B. Now it's AA, because it's the norm of the out state. Then, as you can see, the numerator is actually like it's just a disk conform function. It's crossing symmetry, but the denominator is actually depends on the channel you consider. Because if you choose the T channel, the line should go like this. And because of that, S matrix of theta, it gets an extra factor, which basically is given by square root of the ratio of the networks of lines. And then these networks of lines, you can actually evaluate using TQFT in a fusion category, and that precisely gives you the factor that we observed. So this basically tells you that in some cases, especially in the IR dynamics is non-trivial, there is an additional subtlety in taking the flat space limit. So probably this might be teaching us something about some subtlety about taking the flat space limit of gravity or gauge theory, in which IR is known to be non-trivial, especially in DCO 4. Yeah. Okay, I finished the derivation, so that's the end of my lecture.